I bet you didn't know that the Earth isn't the center of the universe, and neither are we. In the grand cosmic ballet, Earth's just another dancer. The Copernican Principle tells us that humans don't hold a privileged spot in the universe, named after Copernicus, who argued that the Earth moves around the Sun. This principle extends that idea even further. It means our observations from Earth are pretty average compared to any other location in the universe, so no special treatment for us. But wait, while the Copernican Principle has never been proven, and in the most general sense cannot be definitively proven, it remains a cornerstone in the field of modern physics. This principle is implicit in many contemporary theories, especially those in cosmology. Often, cosmological models are developed with the cosmological principle in mind, a broader concept that includes the Copernican principle. Testing these models indirectly tests the validity of the Copernican principle. Before the term Copernican principle was even coined, humanity held several incorrect assumptions about our place in the universe. We once believed in geocentrism, the idea that Earth was the center of everything. Later, heliocentrism placed the Sun at the center, and still later, galactocentrism placed the Milky Way at the universe's core. Each of these assumptions was ultimately disproven. The Copernican revolution was a pivotal moment, showing that Earth is just one of many planets orbiting the Sun. Edmund Halley introduced the concept of proper motion. William Herschel discovered that our solar system is moving through the Milky Way galaxy. Edwin Hubble later demonstrated that the Milky Way is merely one of countless galaxies in the universe. These observations and discoveries have shaped modern cosmology, leading to the Big Bang theory and our current understanding of the universe. Recent and ongoing tests relevant to the cosmological and Copernican principles include examining the time drift of cosmological redshifts, modeling the local gravitational potential using cosmic microwave background (CMB) reflections, and studying the redshift dependence of supernova luminosity. Other tests involve the kinetic Sunyaev-Zeldovich effect in relation to dark energy, the cosmic neutrino background, and the integrated Sachs-Wolf effect, which tests the isotropy and homogeneity of the CMB. Some researchers argue that the KBC void challenges the cosmological and Copernican principles, while others maintain that it is consistent with these principles. Hermann Bondi named the principle after Copernicus in the mid-20th century. Although the principle itself dates back to the 16th–17th century, paradigm shift away from the Ptolemaic system, which placed Earth at the center of the universe. Copernicus proposed that the motion of the planets could be explained by reference to an assumption that the Sun is centrally located and stationary, in contrast to geocentrism. He argued that the apparent retrograde motion of the planets is an illusion caused by Earth's movement around the Sun, which the Copernican model placed at the center of the universe. Copernicus himself was mainly motivated by technical dissatisfaction with the earlier system, and not by support for any mediocrity principle. Although the Copernican heliocentric model is often described as demoting Earth from its central role it had in the Ptolemaic geocentric model, it was successors to Copernicus, notably the 16th century Giordano Bruno, who adopted this new perspective. The Earth's central position had been interpreted as being in the lowest and filthiest parts. Instead, as Galileo said, the Earth is part of the dance of the stars rather than the sump where the universe's filth and ephemera collect. In the late 20th century, Carl Sagan asked, "Who are we?" We find that we live on an insignificant planet of a humdrum star, lost in a galaxy tucked away in some forgotten corner of a universe in which there are far more galaxies than people. While the Copernican principle is derived from the negation of past assumptions such as geocentrism, heliocentrism, or galactocentrism, which state that humans are at the center of the universe, the Copernican principle is stronger than acentrism, which merely states that humans are not at the center of the universe. The Copernican principle assumes acentrism and also states that human observers or observations from Earth are representative of observations from the average position in the universe. Michael Rowan Robinson emphasizes the Copernican principle as the threshold test for modern thought, asserting that it is evident that in the post-Copernican era of human history, no well-informed and rational person can imagine that the Earth occupies a unique position in the universe. Most modern cosmology is based on the assumption that the cosmological principle is almost, but not exactly, true on the largest scales. The Copernican principle represents the irreducible philosophical assumption needed to justify this when combined with the observations. If one assumes the Copernican principle and observes that the universe appears isotropic or the same in all directions from the vantage point of Earth, then one can infer that the universe is generally homogeneous or the same everywhere at any given time, and is also isotropic about any given point. These two conditions make up the cosmological principle. In practice, astronomers observe that the universe has heterogeneous or non-uniform structures up to the scale of galactic superclusters, filaments, and great voids. In the current Lambda-CDM model, the predominant model of cosmology in the modern era, the universe is predicted to become more and more homogeneous and isotropic when observed on larger and larger scales, with little detectable structure on scales of more than about 260 million parsecs. However, recent evidence from galaxy clusters, quasars, and type Ia supernovae suggests that isotropy is violated on large scales. Furthermore, various large-scale structures have been discovered, such as the Klaus Camposan or LQG, the Sloan Great Wall U1, 11, the huge LQG, the Hercules Corona Borealis Great Wall, and the Giant Arc, all of which indicate that homogeneity might be violated. On scales comparable to the radius of the observable universe, we see systematic changes with distance from Earth. For instance, at greater distances, galaxies contain more young stars and are less clustered, and quasars appear more numerous. If the Copernican principle is assumed, then it follows that this is evidence for the evolution of the universe with time. This distant light has taken most of the age of the universe to reach Earth and shows the universe when it was young. The most distant light of all, cosmic microwave background radiation, is isotropic to at least 1 part in 1,000. Bondi and Thomas Gold used the Copernican principle to argue for the perfect cosmological principle, which maintains that the universe is also homogeneous in time and is the basis for the steady-state cosmology. However, this strongly conflicts with the evidence for cosmological evolution mentioned earlier. The universe has progressed from extremely different conditions at the Big Bang and will continue to progress toward extremely different conditions, particularly under the rising influence of dark energy, apparently toward the Big Freeze or Big Rip. Since the 1990s, the term has been used interchangeably with the Copernicus method for J. Richard Gott's Bayesian inference-based prediction of the duration of ongoing events, a generalized version of the doomsday argument. While the Copernican principle has been a cornerstone in our understanding of the universe, some physicists and cosmologists have explored models that challenge or even discard it. The Standard Model of Cosmology, known as the Lambda-CDM model, fundamentally relies on the Copernican principle and the broader cosmological principle. However, alternative models have been proposed to address specific issues within the Lambda-CDM framework and to test the robustness of our current understanding. One significant example is inhomogeneous cosmology, which attempts to explain the observed accelerating expansion of the universe without invoking dark energy. Instead, it suggests that the universe is far more inhomogeneous than we currently assume, positing that we exist within an immense low-density void. To align with observations, this model would place us near the center of this void, directly contradicting the Copernican principle. The Big Bang model, another cornerstone of modern cosmology, is sometimes said to derive from the Copernican principle when combined with redshift observations. Yet, even without the Copernican principle, the Big Bang model remains valid. Evidence from the cosmic microwave background, primordial gas clouds, and the structure, evolution, and distribution of galaxies supports the Big Bang independently of the Copernican principle. However, without the Copernican principle, the foundational assumptions of the Big Bang model, such as the expansion of the universe, become axioms rather than conclusions drawn from the principle and observational data. These explorations remind us that while the Copernican principle has guided our understanding of the cosmos, science thrives on challenging and testing its foundational ideas.